We also have spatial domain filtering. I'm going to load up a different image for this. This is a image ray traced on the TAAC, and we'll do a Gaussian filter on it. So we've now smoothed out some of the edges. Now we'll go to the arithmetic functions, which we skipped earlier. Subtract these two images, and we can see the difference between the images is indeed the edges at this point. We also have a full set of logical functions, and, NAND, etc. Let's take a look at some remapping functions. We can do a reflection of the image, in this case about the x-axis. We can do a rotation by an arbitrary number of degrees. It's a two-pass algorithm. TAAC also has certain morphological functions. I'm going to load up that chest x-ray again. These functions only work on binary images, so first I'm going to threshold the image and then go to dilate, and this time I'm going to do the dilation on the right image and send the results to the left side. And dilation is a region growing algorithm. Here you can see the white region over here has been filled in over here, and you can continue in that way to coalesce regions and help identify objects. Similarly, there's an erode capability, which is the inverse of the first, though they're not actually invertible. And in this case, you can see the black regions have grown some, and the white regions have eroded away. The TAAC can also do interactive zooming. I'm going to load up a Landsat photo of Boston, and this time we'll look at the photo interpreted as a full color image. Here we're looking at the red channel. This is the green, the blue, and now we'll look at it as the full color image that it is. Increase the output image size and the zoom factor a little bit, and now you can see we can move this box around and do pixel replicated zoom in real time. Because we do this in software, it need not be a power of 2 to zoom or even an integral power. And furthermore, it need not be a pixel replicated zoom. So for example, we have a bilinear interpolation zoom. Here you can see a smoother image. Also note that because this is a full color image, it has to do the bilinear interpolation in all 3 channels one at a time, and so this would be 3 times faster on an 8-bit image. Or if desired, we can even do a higher order interpolation, such as a bicubic spline interpolation. This will slow down appropriately, but for certain data sets this is a very desirable zoom. TAAC can also do geometric functions. In this case, we're going to do some rubber sheet warping using tie point remapping. Here are a set of 3 tie points. I'll add some others where we can, let's say, identify this point in this image with this destination over here, and one can set an arbitrary number. These functions can be used in other ways, of course, but this is one way of using the warping capability. And now we can either do a linear or a biquadratic mapping. And so the points we've identified get mapped 1-to-1, and the rest, in this case, were linearly interpolated to their new positions. Or we can do a biquadratic mapping for that result. That's a very useful technique for registering images or compensating for warps in, let's say, the shape of the Earth, or in the scanning technique itself. Just briefly, 2 more capabilities I'd like to demonstrate. Load up a new image for this. The first is interactive histogram capability. So as I move this box around, on the right we see 3 different histograms. Let me make the box a little bigger. It need not be square. Histogram for the 3 different channels, the red, green, and blue channel. And underneath you see the mean and 1 standard deviation for each of the channels. We also now have the capability to do region of interest histograms for any polygonal shape. Also note here the extrema of the 3 channels being displayed. The last part of the image processing library that I'll demonstrate is interactive profiling along an arbitrary line. And so you can see the profiles of those 3 channels displayed on the right. Here's a good example of a combination of the TAAC image processing library using some of the functions in our graphics library for doing the line drawing. Next, we're going to move on to the volume rendering toolkit that comes with the TAAC-1. This consists of 2 basic programs. One is called VoxView, which is a direct renderer for volumetric data sets. First, I'm going to load up a set of MRI slices of the brain. In this case, it's 8-bit data. 61 slices, each 256 squared. The program VoxView provides a great many different capabilities for displaying and manipulating this volumetric data, or for that matter, any scalar volumetric data consisting of 8-bit or 16-bit unsigned integer data. Here we see the volume, which I can rotate using the cursor on top of the graphics window. Let me zoom this window up a little bit so that we can see it a little more clearly. The TAAC does have a hardware 2-power zoom capability, and that's what we're using in this case. I'll move this window up and out of the way. And now we can choose an arbitrary slice to move through this data set. In this case, I've selected an orthogonal slice through the left side of the image. And as I push along this slider, that slice moves. We can do this with any of the orthogonal slices of the rectangular solid. Here we're going in from the front of the head. You can go in from the top. We can view this either by doing a nearest neighbor algorithm for selecting the pixels to be displayed, or we can do trilinear interpolation. And here we can see a much smoother display. As we move the object, it reverts back to nearest neighbor automatically, and when we stop moving, it recalculates the trilinear interpolation. We can also do an arbitrary oblique slice. Here, I'm moving an oblique slice in from the corner of the object. We rotate that around a little so we can see it a little more clearly. And then we can change the pitch and the yaw of the slice to an arbitrary angle. Once we have an angle we're interested in, we can push along perpendicular to that plane. I'm going to switch to the front view, and then I'm going to ask for another capability, which is to extract a slice from the object that we're viewing. I'm going to scale up that slice alone, slide it upwards a little bit, turn on trilinear interpolation, and now some of the new capabilities that have been added to VoxView include voxel editing. So for example, I can select read points, and then wherever I move this cursor around the extracted slice, you'll notice in the window below the voxel coordinates, XYZ coordinates of the location are being read out, as well as the value of the individual voxel. Furthermore, we can edit the volume, individual voxels, by selecting a voxel value to overwrite existing voxels. So in this case, I'm going to edit with the value 0, which I've entered here under voxel value. Now I'm going to select write points, and now as I move around this data set, you'll see a very small trail of white dots. That's just the editing color that's used, and when I click that I'm done, these will be changed to have the value that I've put in voxel value, in this case black. You can see these black dots. Furthermore, you can see them here in the original volume. These have actually overwritten the values in the 3D volume and are now, being as we've sliced into this point, they are now in the interior of the volume data set, and we would note them. So you can use this for identifying surface edges, contouring, for just marking data sets, etc. I'm going to reset this entire volume to the original, which means taking away all the sliced values, and show one more capability that the volume slicing mode has, and that is to do thresholding, which is basically a projection of the data above a certain threshold. And so here I'm going to select a threshold. I can select a top and a bottom. I'm going to select a threshold and then hit the button, and then what we'll see is it's stripping away all voxels below the value of 34 in this case. And so what we will see is a better view of the silhouette of the volume when this is done, a view that we did not have previously. And again, if we were to slice into this, it would give us a slightly different view because of that silhouette edge. I'm going to load up another data set now. This is a set of CT slices of a sloth. It's 197 slices, each 128 squared. To demonstrate the next set of capability of this program, which is raycasting through the volume data set. So here we have a sloth torso, and I'm going to do just a little slicing into it. Take a look at there you can see the rib cage, the heart, and various other internal organs. Now I'm going to switch to a different rendering mode. Instead of slicing, we're going to go to raycasting. In this case, we have the capability of projecting rays through the data set, in each case perpendicular to the plane of the screen, and so one can project the ray at an arbitrary angle by rotating the object because the rays are fixed perpendicular to the screen. You'll notice that when we rotate in ray tracing mode, we just display the edges of the cube. That's because it's not possible to keep up with raycasting through such a large data set while we're moving it. And in this mode, we have 4 different rendering models that we can use. The first is texture mapping, which is the same model that we use in the slicing mode. The second is density sum. This sends rays through the volume, and along each ray it sums all the values that the ray intersects. And here we can start to see some of the detail of this particular data set. For certain data sets, in particular X-ray crystallography data, electron density data, this is a more valuable